Now that we have implemented the derivative of the loss function, what we can do is verify empirically that it is working. And what we can do to do that, or to do that verification, is to compare the value of the derivative of the loss function to a numerical approximation, like we have seen in, sorry for that, I think my phone just vibrated. We can do that by using the formula that we used in the video of the numerical approximations for the derivatives. And so what we do is we define this helper operator, let's call it D, and what this will do is it will have this signature, so it's going to have a function f as the left operand, then it's going to take some value a, which is the value where we want to compute the derivative on the right, and then some small step size dx on the left. And this is our utility operator that helps us differentiate functions numerically. Sorry about that. I pressed some keyboard shortcut by mistake. Okay. So what we do to implement this operator is we first need to figure out the 2 points where we need to compute the value of our function, and those are a plus dx and just a, which is a plus 0. So this computes the 2 points. Now I need to apply the function to each one of those, and then we need to subtract them. And essentially what I would want is to insert a minus between the two values, and I can do that with a minus reduction. And then I take all of this and divide it by dx, which is alpha. So this is my operator that does numerical approximations of derivatives. Now what I can do is I can pick some f function, and we do that by, or as an example, we can carry the left argument of the MSE loss function. We pick some value for dx, and we pick some value for a, like we have seen in the video of the numerical approximations. And now what we can do is, for one, we can compute the actual derivative of the MSE loss function on those points. So notice here, this is the 4 that's carried on the left, and in here we have the value a, and that gives us minus 2. Now if this value is correct, then the numerical derivative should be close to that value. And you can see that it is fairly close. And in particular, it gets even closer if we decrease our dx value, which is what we expected. Now we can try some different value. For example, instead of having a 4 on the left, we could have, for example, a 0. And instead of having a be 3, let's say that a gets, I don't know, 2.73. Now the actual value is going to be 546, and the approximate value is what we get if we use our operator. So 556 is fairly close to 546, but it gets even closer as we decrease the value of dx. And that's what we should be seeing. Okay, notice that this is much closer to 546 than what we started with. Now another interesting thing about the derivative, and that is really useful, is that the derivative points us in the direction of increase. So if we have a positive value here, and what's being computed here is, actually, let me do that again. So it's 0, the derivative, and then a, which is 2.73. So because this is positive, the derivative here has a positive value, then what it means is that if I walk right, so I'm at 2.73, if I walk right, the value of the loss itself becomes larger. So the value of the loss itself is this, 7.4529. Now the derivative is positive, so if I take a small step to the right, then this value should increase. So let me take a small step to the right. Notice that from 745, now we are at 750. Right? And now, if I take another small step, we can say that this increases even further. Now let's take some some other values. Maybe, let me think, maybe still 0 over here, but on the right, instead of 273, let's use the value -3. Now this is the value of the loss. It's the MSE loss. But what is the derivative of the function here? Well, it's, let's see, it's -6. It's negative. And because this is negative, what it shows us is that if I decrease this value, then the whole thing will become larger because the derivative is pointing to the left, to the negative values. So if I take, again, the MSE loss on 0 and -3 is 9. But if I make it slightly smaller, and because this is a negative number, what it means is that in absolute value it becomes larger, but the number as a whole is becoming smaller, then the value of the loss becomes even larger because the derivative was pointing to the negative values. So what this shows is that the derivative points in the direction that I should follow if I want to increase my loss. And so in reverse, what that means is that if I go in the direction that is opposite of what the derivative tells me, then the loss function decreases. Notice here, at 0 and -3, the loss was 9. The derivative points to the negative values, so if I walk towards the positive values, then the loss value decreases. And this is a very important idea, that the derivative points in the direction of increase, and therefore if you do the opposite of what the derivative tells you, then you decrease the value of the function. This is really, really, really important. So let that sink in, and we will continue our journey of implementing a neural network in the next video. Bye.